Thank you. Today we're going to talk about some of the AMD tools, both profilers and debuggers. Um, George will be giving the talks on the OmniTrace and OmniPerf tools in the middle of the session. He's been trying to thin out the slides, so we just gave like a 8-hour presentation covering just those two tools. So it's a bit of work for him to reduce the slides to fit into this session today. But these are exciting tools. There's a lot of rich information that they provide to help with code development. To kick off today's session, I'm going to be talking about the Rocprof tool, which has been around for a couple of years. Just a couple things, housekeeping. Slides for all the previous presentations are up in the projects directory. The Rocprof slides are there. We'll get the other slides there shortly. We have the HackMD has more content that's been added for Rocprof and for the profiling tools. And we've fixed some of the small things that needed to be fixed for Lumi that we hadn't caught before. So you see the HackMD in the chat. You can bring that up and you can work on the exercises as we go along. If you like, we will have about 15 minutes after this session to go through exercises and for any questions. So this content for the Rocprof has been developed by quite a few of our staff. What is it? Well, it's a command line front end for the low-level GPU profiling libraries. And although I say it's a command line, its focus is a command line, but there are some tools to get a graphical view of what's going on. And it is the base level of all our tools. It grabs the hardware counters, a lot of the low-level AMD specific information for our hardware. And it's under constant development. So right now we're at Lumi, you're at 5.2.3 ROCm. With each ROCm release, it gets improved, more counters get added. With each release of hardware, the counters have to be modified for the new hardware. So it's under continual development. And it's part of ROCm. It's part of the stack. If you look in the ROCm bin directory, it's sitting right there. So as I said, there is a graphical, visual graphics interface that goes along with Rocprof, and that's our Perfetto tool. It's a open source general purpose tool that we use to view traces. So it's not a tool that we develop, but we leverage it to give you a really good view of the time history of what's going on. So I'm going to show you a slide that we have at the start of a lot of our profiling presentations. Give you an idea where to use these tools because they each have a role, they each have a purpose. So the AMD profilers, Rocprof is the first one, and this is the raw collection of the counters, the hardware counters, producing the traces, getting the data. It focuses on the timings for the kernels, for each kernel, some data transfer times, and then it shows a timeline visualization of what's going on. So this is probably the first thing you want to look at when you're trying to analyze your application. Get a good idea of um, you know good idea quickly of what's going on. And so we return to Rocprof uh, quite frequently after doing a code modification to get an idea of what's happening. The second tool is Omnitrace. That presentation will follow this one, and it provides the capability of Rocprof plus more. So it also grabs a lot of information from the CPU for MPI. It has a sampling collection tool and many other tools that will supplement the in, uh, the AMD specific information that's coming out of Rocprof, and it supports quite a few different programming languages and APIs. Um, Again, it's a timeline focus tool, and you can visualize this with Perfetto. But as you see in the bottom image, there's a lot more information, uh, you know, a lot of different things being shown on the timeline. And so it provides a lot of rich sources of information, and you can select what information you want for your particular run. The third tool is OmniPerf, and this one is also shows the hardware counters, but this is designed to sort of give you a view of what's happening in the processor. So as you see in the image on the lower right, it's showing from right to left the data being moved into the processor through the from the GPU interfaces from the other GPUs and HBM into the cache system uh, and into the processors. And so it's telling you, are you using all of the processors? Is it, what is the usage of L1 cache, L2 cache look like? And so that can really help you understand what's going on for your whole program or for a particular kernel. It also has a lot of different data that it reports. So it's hundreds of lines of output that shows you what we call speed of light, which is what percentage of the peak capability are you getting for each of these different items. It shows roof lines. It shows um, this simple GUI interface where you get a visual idea of what's happening within the processor. You can also collect the data into a database and then display it with Grafana, which is another open source tool. Um, so why do we have all these tools? Well, you you have different goals when you're using a profiling tool. One of your goals may be where do I want to spend my time today trying to improve the performance. The other may be, just how are how well are you using this GPU, and uh, and specifically, the unique characteristics of the AMD GPU, and so you have different kinds of objectives when you use these tools. So, uh, your approaches are different because of that. You may want timelines. You may want, what your uh, hardware counters are showing for your L1, L2 performance. You may want a roofline plot. And in the past, you always had to go down to do this with Rocprof. While it was possible, it's a heavy lift. That's a lot for one tool to do, and it doesn't really It's not customized to supply all those different needs. And so now we have two new tools, and so they give you different options and a much richer view of things for particular purposes. But I'm going to talk about Rocprof today, and that is quite often the most frequent tool used because it's quick to use. It gives a high level view, and often that's enough to know what to work on next. There's a few options that are used, and really you can see the full set of it with the -H option on it, but the ones that are most often used are these HSA trace, um, HSA trace option, hip trace, rock TX trace, which is for if you place markers in your code, you add a line of code that says, here I am for this routine, it will show it on the output. So and then even the GPU driver calls through the KFD layer. So you can choose what layer to use. You can do more than one, and sometimes programming language or compiler, it's best to use the hip trace. Sometimes it's the HSA trace, but you can use both of them in the same run. So you get the basic information you get out of Rocprof is the kernel execution stats. It's fairly bare bones. It outputs a CSV file that you can bring into Excel or some other spreadsheet or other tool, and it just really shows you how much time you're spending in each kernel. And as you see, it's going to show the most expensive kernel first. So this tells us we should look at these top 3 kernels because they're the ones taking the most time, and perhaps we start out with the Jacobi kernel. It so this one doesn't show a whole lot more information, but that's quite often enough to get you on to the next step. You do see how many times each were called. You see the average time and the percentage of the total time of the run. So I mentioned earlier that you can choose which type of calls to trace. Here we see hip trace, HSA trace, which is the level below hip, and some compilers go directly to the HSA. So it's good to combine hip trace and HSA trace if you don't know what you need. And as it says, the OpenMP offload with some compilers to HSA trace is the right one to use. So we also get a JSON file, and that JSON file, we can take that and view it in Perfetto. Perfetto is built into the Chrome browser. So if you go to this address in the Chrome browser, it's going to pull up that interface. You're not going out to the web. You're just pulling up that interface to show timelines. And it's a built-in tool for Android profiling. So in this case, we're using it for our applications, but its primary focus is for Android profiling, so that you can bring back the performance data from those applications on that device. So Perfetto will come up and you get a navigation screen on the left of Perfetto, and you can open the trace file. I also, it's just not quite here. Down here is selection which will show you the navigation options, and it will show you which keys to zoom in, zoom out, move right and left, which we'll mention here, but it's always nice to have that because you may need a reminder when you bring it up. So the actual timeline screen looks like this part on the center and right, and each line is showing a different aspect of performance. You can expand those to see more detail. You can zoom in, and as you zoom in, you'll see more detail. You'll see the name of the routines. So here we're showing the hip activity. We have other views here that show us GPU activity, and then data transfer. And initially, quite often, you're most focused on data transfer. We know what is slowing down my code because I'm having to transfer data back and forth between the host and the device. So host to device and device to host. As you zoom in, you can see the individual events. And we use the WASD keys to move around. So you zoom in with W and zoom out with S, move left with A, and move right with D. So fairly simple navigation once you know those keys. So we can also get what's happening with each kernel and the dependencies, or what's called here the flow events. So we can see that that hip launch leads to the Jacobi iteration kernel. If we click on that kernel name, we can get more detail, or this little up arrow or caret at the bottom right will give you more detail as well. I would never have found that if somebody hadn't pointed that out. But it pops up a really nice screen which shows you a lot of data, how long that kernel took to operate, how many times it's called. I'm sorry, maybe it doesn't have that. It has the vector register count. It's just off screen here. You have to scroll down when you're in this. Many other details about the kernel. So that can be really, really helpful. And then you can see the flow events if you select that. So we can also add markers, and these are simple lines of code you add. If you have a timing routine in your code, with names for the timers, you can put that in your code and get, with just a few lines, you can get a lot of detail about what's happening on the trace. So we've got a question: does HSA trace capture any kind of memory copy? I believe it does. It shows lower level calls. And I'd have to double check that, but I believe it shows the data transfers. We do have tools that show that. I just don't know if that one, HSA usually shows that. So we can find out what our hardware counters are for this particular device and release of ROCm. So we have quite a few different counters, and you may not know what to start with because there's so many of them. The first thing you want to understand is whether you're worried about floating point performance or memory performance, and then select the appropriate set of counters to start understanding it. Now, all profilers and hardware, you can only collect a small number of counters with one pass of the code. So profilers will do multiple passes to get all the information that you request. So in our example that we have in the tutorial, it makes 3 passes of the code to collect the requested counters. And if you have too many or conflicting, you'll get an error. Um, so you can experiment with how many you can do. But it's generally good to start with a small set first. Also use a smaller problem first because you're going to be running it multiple times. People tend to just take their standard benchmark and try to profile it, and it takes way too long to get the information back. So start small and then add to it. Um, Now, because it's doing multiple passes, it really only makes sense if you have uh, a the same code path every run. So if you don't have a deterministic code where it always follows the same path, there are some issues in whether the data is valid or you can make sense out of it. Maybe you still can, but uh, that it is really important and that it is deterministic. If it's not, it may either be invalid or you have to you get small discrepancies in the results depending on what level of determinism you have in the code. So if you've got a random number generator, you may want to set the seed so it's always going through the same path, or always set it to 0.5 so that you have a deterministic path. So there is a memory limit in the Chrome browser, and it's nominally 2 gigabytes, but we actually reached that limit much earlier. But there is a way to read in the trace before you start up the browser. And so here's the process that you can use to uh, to load that trace before you start up the browser on Linux and on Windows. Um, we're still experimenting with this and seeing just how large a file we can use. And this is Dave, Daniel Dunning of HPE had been experimenting with this, and we've also had a couple of people on the AMD team looking at it. So um, it's a fairly simple process. If you reach a limit, this is one way to get around it. You can also set some environment variables which collect less information, or you can shrink down your the run you're doing to do less iterations or less things before you start the profiling. And I really do suggest that you go with as small a problem as you can for profiling, because you get so much information on that timeline, you can't tell what's going on. So it's easier to analyze if you have less things there. Okay. So here are some of the more commonly used GPU counters. So you might start with some of these and maybe pick the ones that are showing the memory or the floating point instructions. So the first two are showing the vector uh, arithmetic logic units. Um, the uh, the rest of them are showing what's happening in the memory units. So there are a full set of descriptions of the different hardware metrics. It's a fairly long list though, so start small. Um, so um, your GPU hardware counters are global. Right now, we're collecting it for the whole run of the program. It's best if you're doing exclusive use of that node so you don't accidentally pick up information from other things going on. Uh, you can, just get the base names. These options that shorten the names of the kernels can be very useful, particularly in C++ code. And then if you want to get the timestamps on the kernel's durations, you can run it with timestamp on, and you will see this dispatch begin, and you can compute how long each kernel takes. And the stats option does that for you and shows it in the results.stats.csv file. And it's aggregated, so it's over the whole run. So for MPI applications, there is a way to aggregate from multiple MPI ranks. It's a little involved. It needs a little helper script. I would advise starting out with a single GPU, single node run, so that you're not having to also understand what's happening with MPI, and start with that for your optimization, and then add the MPI as you after you've optimized the basic kernels. And I should note the last line here, multi-node profiling isn't supported. So this is MPI within a multi-GPU node. So this is the helper script. You'll notice that it basically puts all the data in its own directory, and then it will merge them. So whenever you're using a profiler, you do have to at least be thinking a little bit about the profiling overhead. There is an overhead. It's generally very, very small, but if you get, a small overhead in a key routine, which is called very, very frequently, it may mean that the overhead becomes significant. So you may want to keep an idea of, how much your runtime is increasing as you add more hardware counters or more markers. I think the bigger limit generally is that there's a limit to how much you can visualize. The traces get too large. While we can take steps to view larger traces, you just can't tell what's going on because there's the timeline is way too detailed, and trying to figure out where to zoom in for the important information becomes difficult. So Rocprof is open source. It's part of the AMD GPU software tools, and this is a production tool distributed with ROCm. Many other tools are using Rocprof, and we'll talk about some today, but there's also HPC community tools that are generally available across all the platforms that also call Rocprof, or some similar layer in the AMD software stack. And so it's a tracing kind of utility for the graphics visualization, and it provides text-based output for quick understanding of what's going on. So with that, we're at the end of the presentation. I will stop the sharing.